Now we will have a discussion on relativistic quantum mechanics, one of the most contemporary branch of physics, and this study as per our syllabus will help you to have your first step towards this most contemporary branch of physics, relativistic quantum mechanics. We know that all that we do in physics in quantum mechanics is the formulation of the Schrodinger's equation satisfied by the system under consideration, which will be having the general format minus h bar square by 2m del square plus v, this is the Hamiltonian, operating over the assumed wave function satisfied by the system is equal to the energy eigenvalue E times the wave function psi. Once we look at this equation, even in the first look itself it's clear that the equation will not be satisfying the Schrodinger's, the relativistic requirement. The first and foremost relativistic requirement for an equation to be viable under a relativistic transformation is that the equation must satisfy the Lorentz covariance, or it must be invariant under Lorentz transformation. The format of the equation must be the same in terms of two reference frames, which are such that one of the frame is moving with a velocity closer to the velocity of light in free space with respect to the other reference frame. This requirement for the equation to be relativistically viable, or it is to satisfy the Lorentz covariance condition, is that the footing of the space and time coordinate in the equation must be the same. Once you look at the Schrodinger's equation, we have the space dependent operator or space coordinate dependent operator del square, which is a second order operator as long as the space coordinate is concerned. Whereas the energy operator, that is always IH cross dou psi by dou t in quantum mechanics, has a order that is 1 or first order in time. So the Schrodinger's equation is second order in space and first order in time. Such an equation will never satisfy the Lorentz covariance condition, so that the Schrodinger's equation cannot be taken as a relativistic equation satisfied by those microscopic particles that are moving with velocity closer to the velocity of light in free space. And of course, you can apply this equation to those quantum mechanical systems that are moving with a velocity that is extremely smaller comparing with the velocity of light in free space. However, we will be talking about such submicroscopic particles that often have a velocity closer to the velocity of light in free space as long as quantum mechanics is concerned. So we always require an equation that will be satisfying the relativistic condition. Another requirement for a relativistic wave equation is that it must be consistent with the space-time coordinates of relativity, or the four-vector formulation of relativity, or the Minkowski space formalism of relativity. As you know, in relativistic mechanics, the space and time coordinates are taken as a single coordinate system with 4 different coordinates. These coordinates are 3 space coordinates x, y and z, and the fourth one happens to be the time coordinate set t. For symmetrical footing, we will be taking this time parameter as say ICT. So the equation must be consistent with the space-time formalism of relativistic mechanics. And once you look at the Schrodinger's equation, this also do not satisfy the consistency with the 4-vector formalism or the space-time formalism, because the 3 vectors coming in this system happens to be the space coordinate dependent vectors, and the 4th vector happens to be the time coordinate dependent vector. However, here also the space coordinate is second order, whereas the time coordinate is first order. So such an equation cannot be taken as a relativistic equation. And it's inevitable that we will have to search for relativistic equation since quantum mechanics is a branch where we will be always talking about microscopic systems that are having velocity closer to the velocity of light in free space. Because of these drawbacks, of course, further there is one more drawback. The Schrodinger's equation cannot explain the hydrogen atom problem in the relativistic regime. Because of these drawbacks, people have been in search of a relativistic wave equation in quantum mechanics, and that can be achieved following 2 mathematical procedures. Once you make a first look for the search of a relativistic wave equation, the first approach is that use of a relativistic Hamiltonian. Instead of the Hamiltonian formalism we have already followed, if we take a relativistic Hamiltonian from the 3rd fundamental postulate of quantum mechanics, the quantum mechanical operator corresponding to a classical parameter or a dynamical variable could be obtained by replacing the relevant dynamical variables in the classical equation by using the quantum mechanical operator corresponding to it. So once we make such a formulation, of course we will be capable of having a relativistic wave equation. Another trial is that, but however, though we can make use of the 3rd fundamental postulate of quantum mechanics, there will be some limitation, because the relativistic expression for energy is E is equal to square root of P square C square plus M square C power 4. This involves this operator, say square root. You cannot omit this operator square root without squaring the equation. But once you square this equation, in order to obtain the energy in the end, of course you will have to take the square root of the equation. Once you evaluate the square root as an energy parameter, there can be a positive square root as well as a negative square root, and this negative square root will eventually indicate to a negative energy, occurrence of a negative energy for a free particle. That is against the concepts of physics. So it will be very difficult to go with such an equation. Of course, there have been a first trial for a relativistic wave equation in this format, making use of a relativistic expression for energy, and with the help of the 3rd fundamental postulate in quantum mechanics, the corresponding quantum mechanical operator, Hamiltonian operator, could be obtained. Schrodinger himself made that trial. However, in the interpretation, he came across this negative energy, or the occurrence of this negative energy, and associated with that occurrence of negative energy that we are going to discuss very shortly, there have been a lot of problems, and because of these problems, Schrodinger himself put aside this equation. By that time, another scientist, Dirac, P.A.M. Dirac, introduced a new theory, a new wave equation, which is first order in both space as well as time coordinates, and that has found a lot of qualities. And by that time, 2 eminent physicists, Weisskopf and Pauli, revived the Schrodinger's assumption of obtaining a relativistic wave equation with the help of a relativistic Hamiltonian by clearing or by omitting the drawbacks associated with that equation. And in this manner, we have two different choices of formulating relativistic wave equation. These are the first one, making use of a relativistic Hamiltonian, and this equation was later on put forwarded by Klein and Gordon. Though Schrodinger has found it for the first time, he was reluctant to publish this result because of the threat that he might have faced due to the drawbacks of the interpretation problem. And this first approach later on revived with the help of Weisskopf and Pauli interpretation by Klein, Fogg and Gordon, and this equation later on became well known under the title Klein-Gordon equation, which is a second order equation in the sense that the equation is second order in both space and time coordinates, unlike Schrodinger's equation. And Dirac introduced a first order theory under the title Dirac equation as a supplementary theory for Dirac equation being satisfied by spin half particles having zero rest mass. A new first order equation have been introduced. This is referred to as the Weyl equation. Both or all these three equations are now in use. Klein-Gordon equation is the relativistic wave equation satisfied by spinless particles that are charged. For example, kaons and pions, these are mesons. So, Klein-Gordon equation or the so-called KG equation is the relativistic wave equation satisfied by spin zero particles, whereas Dirac equation is the relativistic wave equation satisfied by subatomic microscopic particles having spin half and having a non-zero rest mass. For example, electron will be satisfying the Dirac equation, while Weyl equation is satisfied by spin half particles having zero rest mass. For example, this is the equation satisfied by neutrinos and antineutrinos. Now we'll move on to the Klein-Gordon equation. We'll be discussing the formulation of Klein-Gordon equation, then the achievements or the drawbacks associated with Klein-Gordon equation, how these drawbacks have been resolved, and how the theory become triumphant as a relativistic theory being satisfied by spinless particles having charge. Then we'll be focusing on Dirac equation, and after that we will be focusing on Weyl equation. The derivation of the Klein-Gordon equation. I have already told you this is in view of using a relativistic expression for energy. We know that the format of the wave equation, whether it is relativistic or non-relativistic, is always E psi equal to H psi. Now in this case we will have to make use of H as a relativistic Hamiltonian, and E is to be replaced with the help of the corresponding energy operator E equal to IH cross dou psi by dou t, or E equal to IH cross dou by dou t. Now we are in search of a relativistic Hamiltonian. For that we make use of the relativistic expression for energy E equal to square root of P square C square plus M square C power 4. The corresponding quantum mechanical operator could be obtained by replacing the dynamical variables in this equation, that are energy, momentum, and that's all. M and C are constants having the usual meanings. So these dynamical variables are to be replaced by means of the corresponding quantum mechanical operators. However, this involves a square root as an inevitable part of the equation. However, it will be very difficult to go with this square root. So in order to get around this difficulty, of course, we will be squaring the equation. Then we obtain E square equal to P square C square plus M square C power 4. Then the corresponding operator will be energy operator Hamiltonian square equal to momentum operator P square C square plus M square C power 4. Now we make use of this format as E square equal to H square and operate over the assumed wave function, that is E square psi equal to P square C square plus M square C power 4 operating over psi. Here E square and this quantity within the bracket is to be taken as the corresponding operators. So we replace E by means of the corresponding canonical operator IH cross dou by dou t and P as a minus IH cross grad. E square has the meaning of E operating over E again, that is IH cross dou by dou t operating over IH cross dou psi by dou t equal to, as E square is a constant, let me take it C square first, minus IH cross grad is the operator for momentum operating over minus IH cross grad plus M square C power 4 times the identity operator can be there because M and C are constants operating over psi. I square minus 1 H bar square dou square psi by dou t square, as these are constants they can be taken out. IH cross and IH cross are multiplied. Dou by dou t operating over dou psi by dou t is dou square psi by dou t square equal to minus I into minus I, make it say plus I square which is minus 1, H cross into H cross square C square del square plus M square C power 4 operating over psi. Now we divide this equation throughout by means of minus H bar square C square. Then this becomes minus H bar square on the left side vanishes, 1 by C square dou square psi by dou t square equal to, this coefficient vanishes, del square M square C power 4 by minus H cross square C square, 1 C square vanishes, minus M square C square by H cross square times psi. For rearranging, by taking this time dependent term to the right side and this constant to the left side, we make it say del square minus 1 by C square dou square by dou t square operating over psi equal to, this term upon taking to the other side make it say positive M square C square by H cross square psi. Now the quantity in the bracket is an operator, as you know, it is the D'Alembert operator. I will be using this symbol for D'Alembert, a square with a square symbol, and this is a square operator that is always Lorentz invariant or invariant under Lorentz transformation, or will be satisfying the Lorentz covariance condition. Del square psi equal to M square C square by H cross square is a square constant, so we make it say K square psi. For del square or D'Alembertian minus K square psi equal to 0. Now you look at this equation. This equation is second order in the space coordinate del square and it is second order in the time coordinate dou t square as well. So this has a symmetrical footing. And once again, D'Alembertian is an operator that satisfies Lorentz covariance. K square is also a constant that always satisfies Lorentz covariance. So depending upon the quality of the wave function psi, this can be Lorentz invariant or not. It will be satisfying Lorentz covariance if this is mathematically a scalar or a pseudo-scalar. But the operator part is Lorentz invariant, so this is a potential choice of relativistic wave equation. So the qualities are, they satisfy the Lorentz invariance. It can be viewed in terms of the symmetrical ways in which the space and time coordinates occur in this equation. Both the space coordinate and the time coordinate are second order and has symmetrical footing. So this will be satisfying Lorentz invariance. And D'Alembertian and K square, which is a constant, both are satisfying Lorentz invariance. So depending upon whether the wave function psi is a scalar or a pseudo-scalar, this equation will be satisfying the Lorentz covariance condition being satisfied by a relativistic wave equation. And once again, it is consistent with the space-time coordinate formalism or the Minkowski space formalism of relativistic mechanics. We will be seeing this very shortly in the next slide. But I can tell you that this is consistent with the momentum for vector formalism in relativistic mechanics. In relativistic mechanics, momentum can be taken as a 4 vector with its 4 different coordinates being the space-dependent 3 coordinates p mu represented by minus IH cross dou by dou x, minus IH cross dou by dou y, and minus IH cross dou by dou z respectively. And the 4th component of momentum happens to be having a relationship with energy as IE divided by C. This is the 4th component of momentum, P4. As you can see, P mu is equal to P mu, where mu is varying from 1 to 3, with E1 being Px, P2 being Py, and P3 being Pz is equal to minus IH cross dou by dou x mu. When mu is 1, x mu is x itself. When mu is 2, x mu is y. And when mu is equal to 3, x mu has the meaning of z. This has the representation, say, minus IH cross grad, with grad having 3 different components, dou by dou x mu, dou by dou, with mu varying from 1 to 3. And the 4th component happens to be P4 is equal to, as I have told you, this is IE by C. That is I by C into E, energy. Energy in quantum mechanics is IH cross dou by dou t. Now let's take this I in the numerator to the denominator. I in the numerator is minus I in the denominator. So this is equal to minus I is already there as IH cross is there in the numerator. And we take this I to the denominator to make IC in the denominator. And we put this IC along with time coordinate. Then this becomes IH cross dou by dou ICT. ICT is the 4th component of position, time, or space-time coordinate. So I can represent this as a x4. This is equal to the 4th component of this space-time coordinate, say x4. So this is equal to minus IH cross dou by dou x4. And is consistent with this representation, momentum equal to minus IH cross dou by dou x mu. If you incorporate the 4th component, we can represent this as a momentum having 4 different components, or as a 4 vector minus IH cross dou by dou x nu, with nu varying from 1 to 4, or of course in some textbooks this is being represented as a 0 to 3. Then the 0th component will be taken as the time component, and in 1 to 4 representation the 4th component is taken as the time component. So this equation is consistent with the space-time formulation of relativistic mechanics. Now we have the equation del square minus k square psi equal to 0, or D'Alembert square minus k square psi equal to 0, or D'Alembert psi equal to m square c square by h bar square psi. D'Alembert has this space-dependent term del square, which is dou by dou x mu operating over dou psi by dou x mu, plus we take minus 1 as say I square, and I square is written in the denominator to make it say plus 1 by I square c square dou square psi by dou t square equal to k square psi. dou by dou x mu operating over dou psi by dou x mu plus dou square psi by dou ict square. I square c square t square is the, we make it ict whole square, the fourth component of space-time coordinate square, equal to m square c square by h cross square psi. That is dou by dou x mu of dou psi by dou x mu plus dou by dou x4 of dou psi by dou x4 equal to m square c square by h cross square psi. Or dou by dou x nu of dou psi by dou x nu equal to m square c square by h cross square psi. And this is the covariant tensor representation or covariant representation of plane and Gordon equation. Covariant representation of plane Gordon equation give us the idea that it is invariant under Lorentz transformation, or this satisfies the Lorentz covariance condition being satisfied by a relativistic wave equation. Now the major drawbacks that we have to discuss associated with this theory. We have seen that this equation is second order in both space as well as time. For an equation to satisfy the dynamical postulate being satisfied by any equation of motion, the equation must be first order in time. The dynamical postulate states that if the equation of motion satisfied by a system is first order in time, then by knowing the features of the system at any instant of time, the features of the system at an earlier instant of time can be evaluated, or the features of the system in the future can also be evaluated. However, for this to be satisfied, the equation must be first order in time, as you have seen it in Newton's laws of motion, F equal to m into dv by dt, which is first order in time, or as you have seen it in the case of the Lagrangian formulation, d by dt of dou L by dou qj dot minus dou L by dou qj equal to 0. This also has first order time derivation. However, the Klein-Gordon equation involved the second order time derivative, so that the dynamical postulate is no longer valid. You cannot tell the future or the past of the system by knowing the present of the system. And for the derivation, the second drawback is that for the derivation of the Klein-Gordon equation, we have inevitably made a squaring of the corresponding relativistic expression for energy, because this involves a square root operator. To get around this square root operator, we have squared it. And the act of squaring must have introduced a drawback. Once you solve the equation, you will be getting the square of energy eigenvalue. Then to interpret it as energy, inevitably you will have to take the square root. Once you take that square root, you will come across both a positive square root and a negative square root, even for a free particle. A free particle with a positive energy is valid, but a free particle with a negative energy is very difficult to interpret. So there will be the occurrence of a negative energy for a free particle as long as the interpretation of Klein-Gordon equation is concerned. We will now physically verify it. Energy eigenvalue of Klein-Gordon equation is to be evaluated. For that, we have the Klein-Gordon equation del square psi minus 1 by c square dou square psi by dou t square equal to k square psi. This equation has a homogeneous part, that is D'Alembertian psi equal to 0, and which is basically a plane wave equation, and the solution is an exponential parameter, that is a e raised to I by h cross into p dot r minus et, where p is the momentum and e is the energy. As long as a free particle is concerned, these are the only two parameters possessed by it, or at least these are the only two parameters known to be possessed by a free particle at that time. That was in 1900 to 1920 of duration. So psi equal to a e raised to I by h cross into p dot r minus et. If you like, you can take this h cross to the bracket then this becomes a e raised to I into p by h cross dot r minus e by h cross into t. P by h cross is the wave vector k and e by h cross is the frequency omega. Then we replace it as psi equal to a e raised to I by h cross into k dot r minus omega t. Now differentiating this equation twice in space to obtain del square psi, that is dou by dou r of dou psi by dou r. That is dou by dou r of dou psi by dou r will be derivative of this one with respect to position. A e raised to I by h, a is a constant. Derivative of a is a constant. Derivative of exponent term, that is exponent itself. Then there comes psi. Now derivative of this function of function I by h cross into p dot r minus et. That is I by h cross into p. Dou r by dou r is 1, and this is independent of position coordinate, so there is no contribution. So dou psi by dou r is derivative of this one psi itself into I by h cross into p. Now again we take derivative. I by h cross into p is constant. Dou psi by dou r is again I by h cross p into psi. To make it say I by h cross p into I by h cross p, that is I square by h cross square p square. I square is minus 1 minus p square by h cross square psi. Similarly, we evaluate dou square psi by dou t square. That is dou by dou t of dou psi by dou t. Dou psi by dou t is derivative of a e raised to I by h cross. A is a constant. E raised to I by h cross has a derivative, that is exponent term itself, e raised to I by h cross into p dot r minus et into derivative of I by h cross into p dot r minus et. That is I by h cross into minus e minus ie by h cross. So derivative of psi with respect to time is psi into minus ie by h cross. Again we take derivative psi constant ie by h cross into ie by ie by h cross is constant minus ie by h cross into derivative of psi is minus ie by h cross into psi itself. So we have minus ie by h cross whole square. Make it say minus minus, make it plus I square minus 1 minus e square by h cross square psi. Now we substitute this in the Klein-Gordon equation. Del square psi minus 1 by c square dou square psi by dou t square equal to m square c square by h cross square psi. Del square psi is minus p square by h cross square psi minus 1 by c square, and minus e square by h cross square make it say plus 1 by c square e square by h cross square psi equal to m square c square by h cross square psi. Or multiply this by h cross square c square, that make it say minus p square c square plus e square equal to m square c power 4. And psi will be vanishing as these are no longer operators. P is momentum parameter being evaluated and E is the energy of the free particle. That is E square equal to, take minus p square c square to the right side, p square c square plus m square c power 4. This is nothing new. This is nothing other than the relativistic expression for energy, of course, as long as a free particle is concerned. But what about the energy? That's equal to root p square c square plus m square c power 4. And this can have a positive square root, also a negative square root. Let this magnitude p square c square plus m square c power 4, the square root of p square c square plus m square c power 4 is EP, then the energy is plus or minus EP. And then the wave function can have two different choices corresponding to positive energy plus EP. There can be a solution psi plus equal to a plus e raised to I by h cross p dot r minus EP into t, where EP positive magnitude is taken. And corresponding to negative energy minus EP, the solution is psi minus equal to a minus e raised to I by h cross into p dot r minus EP is taken overall, then there will be plus EP into t. So there can be two different solutions for the free particle. Then of course, for the superposition principle to be obeyed by the wave function, the most general solution will be a linear combination of these two counterparts of solutions. Now we'll consider the equation of continuity. Equation of continuity is to be satisfied by any dynamical equation of motion, and always we evaluate this equation of continuity to evaluate the position probability density as long as quantum mechanics is concerned, and we require this position probability density to be a positive definite quantity because it is a measure of probability of finding the system that needed to be always positive. We cannot go with the idea of a negative position probability density. And of course, we cannot go with an idea of negative energy also as long as a free particle is concerned. We expect only free particles having positive energy. The physical interpretation of a free particle with negative energy is meaningless. So we have already come across a negative energy, occurrence of a negative energy free particle as long as the Klein-Gordon equation is concerned. Now we will look into the second drawback, in fact, as long as the Klein-Gordon equation is concerned, that is the occurrence of a negative position probability density. To evaluate that, we will have to first of all identify the equation of continuity. There is a textbook track for the equation of continuity to be evaluated for any dynamical equation. That is, you have to take the equation, then its complex conjugate, multiply the equation by psi star and the complex conjugate of the equation by psi and subtract them. That will eventually lead you to the derivation of the equation of continuity being satisfied by that wave function or by that dynamical equation. For that, we consider the Klein-Gordon equation. We take the complex conjugate of the equation, del square psi star minus 1 by c square dou square psi star by dou t square equal to m square c square by h cross square psi star. We multiply equation 1, pre-multiply equation 1 by psi star and post-multiply equation 2 by psi and subtract them. Then pre-multiplication of 1 by psi star gives us psi star dou square psi minus 1 by c square psi star dou square psi by dou square psi by dou t square equal to m square c square by h cross square psi star psi, because we are pre-multiplying it. And we post-multiply the conjugate equation by psi, del square psi star into psi minus 1 by c square dou square psi star by dou t square into psi m square c square by h cross square into psi star psi. Now the right side are exactly identical. Upon subtracting, you can vanish these two. To make it exactly identical, we multiply the equation by psi star as a prefactor and the conjugate equation by psi as a post-factor. Subtracting, we obtain this one minus this one, psi star del square psi minus del square psi star psi, and minus 1 by c square will be common for these two terms. Minus 1 by c square is taken out, psi star dou square psi by dou t square minus dou square psi star by dou t square into psi equal to, on the right side, psi star psi minus psi star psi, that is psi square psi, will be vanishing. Now we make use of the identity del dot psi star grad psi equal to psi star del square psi, first function psi star into derivative of second del square psi plus derivative of first grad psi star into second function, that is grad psi. And we require a substitution for psi star del square psi. So we take this term psi star del square psi equal to del dot psi star grad psi minus grad psi star dot grad psi. And once you take the complex conjugate of this equation, we obtain it del dot psi grad psi star equal to psi grad psi star, del square psi star plus grad psi star complex conjugate, that is grad psi, dot grad psi complex conjugate, that is grad psi star. Now we replace this term and this term with the help of these two equations, we have psi star del square psi equal to del dot psi star grad psi minus grad psi star dot grad psi. So this becomes del dot psi star grad psi minus grad psi star dot grad psi minus this one, that is psi del square psi star is to be replaced. Del square psi star into psi. Psi, this dot product is irrelevant because del square psi star will be always a scalar parameter. Grad psi will be a vector. Del dot grad psi is del square psi, which is the divergence, that will be a scalar. So we need not bother the commutability of this term. This will be always commutable. So this is equal to del dot psi grad psi star, del dot psi grad psi star minus grad psi dot grad psi star minus grad psi dot grad psi star. There is an additional minus because we already have this term say minus. To make it say overall this simple plus. Now this term and this term are identical. Dot product is always commutable. Grad psi dot grad psi star and grad psi star dot grad psi are exactly equal, but they are having opposite signs. So this term and this term will be going. And this one here also we make a substitution. For that you consider dou by dou t of psi star dou psi by dou t equal to first function psi star into derivative of second dou square psi by dou t square plus derivative of first dou by dou t of psi star, which is dou psi star by dou t, into second function dou psi by dou t. So that psi star dou square psi by dou t square, which is to be substituted in this, will be equal to dou by dou t of psi star dou psi by dou t minus dou psi star by dou t into dou psi by dou t. Already we have minus 1 by c square out. We substitute for psi star dou square psi by dou t square, that is dou by dou t of psi star dou psi by dou t minus dou psi star by dou t into dou psi by dou t. There is a minus, we put it say minus. Now we have to substitute for dou square psi star by dou t square into psi. For that you take the complex conjugate of this one and again rearrange. We obtain it say dou by dou t of psi dou psi star by dou t minus make it say plus dou psi star by dou t complex conjugate, that is dou psi by dou t into dou psi star by dou t. So this term and this term are exactly identical with opposite sign. They can be cancelled. Now what remains is a divergent term here and another divergent term here. We can combine them. Del dot of psi star grad psi minus psi grad psi star minus 1 by c square into dou by dou t of this one and dou by dou t of this one. These two terms can also be combined because we have dou by dou t there common. To make it say del dot psi star grad psi minus psi grad psi star minus 1 by c square dou by dou t of psi star dou psi by dou t minus psi dou psi star by dou t, that's equal to 0. Now we multiply this by a constant IH cross by 2m. Then this becomes del dot IH cross by 2m into psi star grad psi minus psi grad psi star minus IH cross by 2m c square. 1 by c square is already there. We multiply it by IH cross by 2m. We already have a minus here. Dou by dou t of psi star dou psi by dou t minus psi dou psi star by dou t. Now here I in the numerator can be taken to the denominator to make it say positive. So we make it say del dot IH cross by 2m psi star grad psi minus psi grad psi star plus we take I in the minus I in the numerator as plus I in the denominator. So we have plus sign here. Dou by dou t of h cross by 2 im c square into psi star dou psi by dou t minus psi dou psi star by dou t. Now this is of the form del dot a parameter plus dou by dou t of another parameter equal to 0. Definitely this parameter is then the current density and this parameter in the time derivative is the source density. the negative time derivative of this flux will give rise to the current along the surface as long as the continuity equation is concerned. Then we write it in the format del dot J plus dou rho by dou T equal to 0, where J is the current of particles as long as a quantum mechanical system is concerned, and the current of particles is at the expense of the position probability density of particles being occupying the volume whose surface will be giving you this current of particles. Then rho has only one meaning, it is a measure of the position probability density of the particles. Now we look into this. Rho equal to h cross by 2I mc square into psi star dou psi by dou. So rho equal to h cross by 2I mc square psi star dou psi by dou t minus psi dou psi star by dou t. We have already evaluated dou psi by dou t and dou psi star by dou t for a free particle. We substitute it here. Before that, we take I to the numerator minus IH cross by 2mc square into this bracket, that is minus 1 by 2mc square into take IH cross to the bracket psi star IH cross dou psi by dou t, minus is already there outside, minus psi minus IH cross dou psi star by dou t, that is minus 1 by 2 mc square into psi star IH cross dou psi by dou t is E psi, and this is the complex conjugate of IH cross dou psi by dou t, that will be then equal to E psi star with plus sign here, because IH cross dou psi by dou t has a complex conjugate which is minus IH cross dou psi by dou t. So we have taken this minus sign also here. So this is the complex, this is in fact minus IH cross dou psi star by dou t is in fact the complex conjugate of this one. That also will be then equal to E psi star. So this is minus 1 by 2 mc square into psi star E psi plus psi E psi star, where E is now a scalar that is taken out. What remains in the bracket is psi star psi plus psi psi star, that is psi square plus psi square 2 psi square, and this 2 will be vanishing to make it say minus E by mc square. But we have seen that E equal to plus or minus EP. So we obtain the position probability density in terms of energy as plus or minus EP by mc square. However, once you look at this expression for position probability density, rho have two different choices. It will be positive when EP is positive, and will be negative when EP is negative. It is very easy to go with a positive position probability density because we actually require a positive definite position probability density. But it's very difficult to go with a negative position probability density because it is a measure of the probability for finding the system, and the probability can never be negative. So this poses an interpretational problem for the Klein and Gordon equation. This was actually faced by Schrodinger himself once he formulated the same equation. It was because of this interpretational problem he put aside the theory without publishing it, and by that time Dirac has introduced his successful theory. Due to the overwhelming success of the Dirac theory, the Klein-Gordon equation has been put aside for nearly a decade. And later on, in 1934 only, Schrodinger introduced this theory, which later on known under the name of Klein and Gordon. As early as in 1916, however, he didn't publish it. Due to or following the revival of the successful interpretation of the theory, it was in 1934 only Weisskopf and Pauli revived the theory with the help of their interpretation. We will now look into this interpretational problem being faced by Pauli and Weisskopf. What they have done is that they multiplied the position probability density by E, the charge. Because charge can have two different options. It can be either positive or negative. So the interpretational problem will no longer be a problem. It is not the position probability density that is being represented. Instead, it is the charge density that is being represented. Now, once you multiply rho by E, we obtain it's a E rho that is being written as a capital rho, which is the charge density here onwards. If it is small rho, it's of course the position probability density, equal to EH cross by 2 IMC square into psi star dou psi by dou t minus psi dou psi star by dou t. When rho is the charge density and J is the current density, then J equal to EH cross by 2 IM into psi star grad psi minus psi grad psi star. It can also have two different choices corresponding to the flow of positive charges and negative charges. Now, rho plus equal to E EP by MC square psi square. This is positive definite already. EP is positive, of course, as we have taken it positive here. So this is now a measure of the positive charge density. And rho minus equal to E into EP by MC square into psi minus square, where EP is negative, so that this represents the charge density of negative charges. And there is one more interpretation being made by Pauli and Weisskopf. The Klein and Gordon equation is del square minus k square psi equal to 0. The operator in the bracket, that is D'Alembert and a constant, are Lorentz invariant. Now psi can have three different choices. When psi is real, then of course rho will be equal to 0. Because for a real parameter, you cannot go with this positive sign here. Minus IH cross dou psi star by dou t will be minus itself, since psi is a real parameter. Psi star and psi will have then the same meaning. Then this will be minus, and this rho will be tending to 0. And the interpretation will be clear then also, because rho can have 0 value also. Then it is an assembly of neutral particles, or a set of neutral particles are being satisfied by satisfying the Klein-Gordon equation. Now, for the equation to be covariant, psi can have two different choices. Psi can be a scalar or it can be a pseudo-scalar. If psi is a vector, there is a chance that this is non-invariant under Lorentz transformation. We require the equation to be satisfying Lorentz covariance. Then psi can have only two choices. Psi can be a scalar or a pseudo-scalar. Whatever may it be, whether it is a scalar or a pseudo-scalar, there are only mesons that satisfy this kind of a wave function, which is either scalar or pseudo-scalar, since they have negative intrinsic parity. So, Klein-Gordon equation, or summing up all these points that Weisskopf and Pauli has introduced, we can say that Klein-Gordon equation is the true relativistic wave equation satisfied by microscopic particles having spin 0, because a wave function that is scalar or pseudo-scalar will be always having a spin, or a particle that has a wave function which is scalar or pseudo-scalar are having spin 0. So Klein-Gordon equation is the relativistic wave equation satisfied by spin 0 particles having charge either positive or negative or 0. For, however, the equation to be satisfied, it must be an assembly of neutral particles. So, if there is positive charges, there must be equal and opposite negative charges as well, occurring as an assembly. This also implies to the concept of the occurrence of particles or antiparticles along with particles. Corresponding to a particle, there occur an antiparticle as well. And later on, in 1936, these pions and kaons having charge K plus, K minus and neutral kaons have been identified, and these particles are having spin 0 as well. They are always satisfying a scalar or pseudo-scalar wave function, are found to be the particles that obey Klein-Gordon equation as the relativistic wave equation. So we conclude Kg equation is the relativistic equation satisfied by spin 0 particles having negative intrinsic parity. This arises from the property of their wave function, and having either positive or negative or neutral charges. Example for Klein-Gordon particles are pions and kaons, which are mesons. Now we move to the operator formalism of Klein-Gordon equation, or rewriting the Klein-Gordon equation in the Hamiltonian format.